and so we're going to a very different, this just speaks to the range of majors we have in honors. So we're going, our first presentation was biocommunication disorders major. Now we're going to a geology major. So we have all kinds of, it's fascinating, just kind of range of projects. Okay. So our next presenter is Adish Bomani, a geology major, and his thesis is titled, it's a new one, titled Evidence for Fluids in Duches County Metamorphic Sequence, an Electron Microscope Study. So we're looking forward to hearing about this, and the thesis is advised by Dr. Jordana Garrett, right here, sitting right there, and also from Cindy Newholtz, and also from Ulrich Bau of MIT. Adish is the current secretary of the local chapter of Sigma Gamma Epsilon, a National Geology Honor Society, and assists the department through community service and teaching assistantships, and has been doing so since his freshman year. Going forward, Adish hopes to further his education in geology at the graduate level, looking for opportunities within the fields of economic geology and mineral resources. And I know you're working on graduate school, and I'm sure you're going to have a very bright future.
Hope so.
In graduate school. Yeah, I'm sure you will. And your parents are here. So
Yeah.
we got that. All right. It's all yours.
Good afternoon, everyone. I am super thrilled to have this many people show up, including a bunch of people who I don't know. So thanks for showing up to my presentation.
That's always good.
Yeah, it's good. I hope you enjoy my thesis here. Big thanks to my parents, of course, for supporting me throughout my college career. Biggest thanks to Dr. Jordana Garrett for not only being my thesis advisor, but also helping me through just academic advising. Has been with me for the past 3 years. So really can't thank her enough. And of course, to my friends who decided to show up as well, thank you guys. I know I've been really wanting you guys all to come, and I'm happy with the turnout. So this is my project, Evidence for Fluids in the Duches County Metamorphic Sequence, a study through electron microscopy. So I know we have a lot of non-geology majors here, so we're going to go do a really quick crash course of a lot of stuff in geology. First things first, the Earth. We live on it, we love it. But we actually live on a very thin portion of it up there. So that very thin line up there, that's our crust. And there's two types of crust. We have oceanic crust and we have continental crust. Oceanic crust, as you imagine, would be found under the oceans, and continental crust is where we're standing on right now. So continental crust, it's less dense, it's thicker. Oceanic crust, it's a little thinner, and it's far more dense than the continental crust. So most of your oceanic crust is made of this black rock here, which is basalt. A continental crust is mostly granite. And then we have the other layers within the actual meat of the Earth there. So we have the mantle, which is this very large layer that's mostly made of this green mineral and rock peridotite, and we have our core, which is mostly made of, we have the inner core, which is a big ball kind of solid iron and nickel, and we have an outer core, which is liquid metal, which actually gives us our nice magnetic field. So the crust is not static, it is moving, it is dynamic, and it's actually broken up into what we call tectonic plates. So tectonic plates are bits of crust that are always constantly kind of moving around. So how do we know these exist, and how do we know where they are? Well, this is a nice map we have here of actually some earthquakes. And you can see that the earthquakes are very clearly kind of outlining some regions, and that's how we can tell where the plates pretty much are. And this is a GPS map that's showing the movement of the plates. So you can see that some of them are moving apart, some of them are moving together, moving past each other. So we have a very dynamic, active tectonic system in the Earth, unlike anything else really we see in the universe. So of course, the speed of movement is quite slow actually, so they move about as fast as your fingernails grow. So of course, since we have all these plates moving around, we're going to have boundaries between them. We're going to have regions where they're moving apart and coming together. So in the middle there, we have a divergent plate boundary, two plates moving apart and creating some new crust in the middle. And on the right side, which is more to our interest today, is a convergent plate boundary. And this is showing a piece of crust that's actually being subducted underneath another piece of crust. And that bit is melting. It's being shunted deeper into the Earth, so there's more heat, there's more pressure. It's allowing for some melts to form, and those rise up and form volcanoes. And in some cases, they can form volcanic island arcs. So we're going to go back about 550 million years ago in about the region where we are in the United States. And we have Proto-North America, and we have an island arc, like I mentioned right there. So very similar situation to what we have here. We have a piece of oceanic crust being subducted underneath that continent right there, and it's melting, forming some island arcs, and it's forming a nice basin right in between. And that basin is prime depositional environment, so sediments that are eroding from the right, from the left, they're all being deposited right in there. So you can imagine that these two are actually moving towards each other. Now they're moving very slowly towards each other, so we're going to fast forward about 100 million years. And oops, oh, what do we have here? It seems to have shunted up on top of the Proto-North America. So we have this tectonic Electron, that island arc that I mentioned before. It's moved on top of our pre-existing Proto-North America. So what does that mean for all the rocks underneath? Well, we have all the rocks that were in the basin on the continent. They are now being subjected to increasing pressure and maybe increasing temperature. When this causes metamorphism, so we see the rocks that were originally there end up changing. The minerals change, their structure changes, their orientation change, and they end up transforming into different types of rocks. So my area of interest is that very thin green sliver right there. So that is what we call the Pohog quartzite. So quartzite is kind of a misnomer for this layer. It should be called a meta-arkos. So a quartzite is, as you might imagine, a rock that is very rich in pretty much just quartz. From our studies, we have found that there is lots of feldspar mineral in this layer, and that means it really shouldn't be called that. But for our intents and purposes today, we're going to be calling it what it's called on the map. So that Pohog quartzite is bounded by two other rock units. We have a gneiss layer at the bottom, and we have a layer of marble on top. So just keep that in mind going through. I just want you guys to have a good understanding of what we're looking at. Oh, there we go. So this is our layer on the map section. The green layer that I showed before is actually that very thin kind of brown area right there. This rock on the right here is about what your Pohog quartzite would look like physically, like if you were to look at it in hand specimen. So what are my goals of this study? Well, I want to take a look at what happened here pretty much. I want to look at the transect of this quartzite, and I want to investigate the metamorphic processes, see if there's any new minerals that have been formed, see like how fluids have played a role in this, and also to see if any of these metamorphic reactions have created new minerals that would affect the strength of the layer. And what I mean by that is, if we have a very uniform piece of rock, the integrity of the rock is much more so than if we had a rock with lots of different minerals growing in there. So if we have one solid piece as opposed to a piece with a lot of different stuff in there, that would definitely be weaker than the solid piece. So we want to take a look at those new minerals, we want to see how fluids assisted in this formation, and we want to maybe think about where the fluids came from. There we go. So of course, to start looking at some rocks, we're going to need some rocks. So we have some pieces that were already collected by the person who was working on this project before me, Mr. Matt Ruggiero. He's currently a master's student actually at Idaho State University. It was very nice to already have these samples collected for us, but we need to have them prepped for the scanning electron microscope. So we sent these off to a lab to be cut down to the right size, and then we have to put them on the polisher. So we have two polishing wheels. We have a lap for alumina, so we put that on. I put that on there for about 5 hours. They kind of just spin around. It looks like a nice little carousel thing. And clean them off, then put them on the silica lap for about an hour. And at that point, they're ground to the right polish that we need for electron microscopy. And the next thing we need to do is actually coat them. So we need the samples to be conductive in order for them to work, in order for us to get a proper image, do scanning and stuff. So we put them in this graphite coating machine. This only takes about 10 minutes. We put them in there. It actually vaporizes some graphite rods and coats the surface with the conductive layer that we can use. So next step, take it to the actual electron microscope here. So this is our lab. This is our lab in the department. That's our scanning electron microscope. So what do we use this for? Well, we want to image it for one, and we also want to find some elemental compositions. We want to see what kind of elements are in there, what kind of minerals. So we can use that. So a quick background on how this machine works. So we have an electron gun up top that has like a tungsten filament that heats up, fires down some electron beams at our sample, and we get some emitted spectra pretty much. So we have a couple different signals here. So we have secondary electron signal that we can use for looking at the surface features. We can use it for imaging. And we have backscatter electron, which captures a larger volume, and we can actually see some more compositional variations using that. And then we have that cool device right there. That's our EDS probe. And that actually picks up emission spectra from the sample. And every element has a unique spectra that it produces. and the machine can read that and display it for us, and so that's how we figure out what elements we have in the sample. So an example of what sort of pictures we get from the microscope, this is in BSE. You can see it kind of gives it to us grayscale, it's not color, but the brighter regions tend to be grains that have more metals in them, and the darker regions are stuff with lighter density. So we have some quartz, we have some feldspar. I think that bright stuff in there is some titanium or iron phase. So this is an example of what I would look at. This is a pretty simplified image. So when you look at this, you go, what is that? Well, we can identify each of these grains. So we can say that light stuff up top is a potassium feldspar mineral. Then we have some quartz on the side there, that darker stuff, and that big bean grain in the middle, that's our apatite. So this is the actual spectra that the machine gives me that I have to go through and kind of identify. So take the very first one, for example. It's giving me a peak for iron, it's giving me a peak for sulfur. What mineral has iron and sulfur in it? Probably pyrite. So that's my job, going through all this and identifying. Just same one on the bottom. Potassium, silicon, aluminum, oxygen, probably potassium feldspar. So I did that quite a lot of times. This is just a little sample of one of my data sheets. We have all the spectra in the middle showing like what percentage of elements we have, and on the right, I pretty much would say like, okay, this looks like this has this elemental composition, it's probably this element. So I did about anywhere from 60 to 100 scans of each sample, and I did about 8 samples. So putting all that together, we had samples numbered from 4-1 all the way to 21. And if you remember before I was talking about the regions being bounded by that gneiss and the marble, this is kind of related to that. So the samples that are lower number are taken closer to the rock that was closer to the gneiss, and the samples at the bottom were taken closer to the marble. So every time you see a green box, that means that mineral was found in that sample. And if you see a red box, that means that mineral was not found in that sample. So you can see in most of these samples, or all of these samples, we have quartz and we have potassium feldspar. Those are the common elements we would expect. Those are our major elements. And we have some other more interesting things that I'll get to as we go on. So here are the formulas for those two. So we have quartz, potassium feldspar, and some of the more exotic minerals. We have chlorite, stillpneumalane, pyrite, hematite, and monazite. I'll actually get back to that one because that one may be important in the future. So I know this might not look like a lot, just the numbers and the data, so this is to give you kind of a good idea what these minerals would look like in hand specimen. A lot of people know what quartz looks like. That's what potassium looks like. Potassium feldspar looks like. It's kind of this cubic pink stuff. And underneath we have what they would look like actually under optical regular light microscopy. So the very first mineral I'm going to start with is potassium feldspar to show compositional trends. So remember, I want to look at what kind of elements it has and how these change as we go across the different samples. So what we see in potassium feldspar is we see an increase in aluminum, and we see, interestingly, a decrease in potassium. So that's interesting. That might come back later. And then underneath we have a chart for iron. We can actually see that iron is increasing. So that's interesting that we find iron in potassium feldspars at all. That's typically not an element that we would see in them. It's very possible that the potassium feldspar is cracked and we have iron minerals forming in between here, and the beam is quite wide, so it's picking up all of these together. So that might be one explanation as to why that's happening. So the next two minerals I want to talk about are pyrite and hematite, which I have a hand sample picture down there. Pyrite's that cubic stuff there. Hematite is the dodecahedral looking stuff there. So we have pyrite, which is iron sulfide, and we have hematite, which is iron oxide. So it's interesting that we find these two together because we have reduced iron and we have oxidized iron together, which is quite uncommon. So why would that be? So I had a hypothesis that maybe the pyrite was actually reacting with some oxygenated fluid, maybe reacting with some minerals around to actually form that hematite. So I went and I started looking through some literature to see if I could find anything that supported my hypothesis, and I did actually find this paper, which is cited there at the bottom, that had that reaction in yellow. So we have pyrite reacting with oxygen to form gaseous sulfur compounds and hematite. So we don't see any other sulfur minerals beside pyrite for the most part, and that actually makes sense with this because all the sulfur, was turned into gaseous sulfur compounds. It left, so there's no other sulfur minerals that we really see. So we have our pyrite, or iron sulfide, reacting with some oxygenated fluid and forming our hematite. So the pyrite is actually the bright green, the brighter stuff up there, and you can see that the hematite is almost like cutting through it like in veins. So that's what really tipped me off to this. So maybe the pyrite is like turning into the hematite. So this is another part that I wanted to take a quick look at. In regions where we have pyrite grains surrounded by quartz, we see a lot less hematite reactions than if we have regions surrounded by feldspar, and this could be that the feldspar is actually cracked and it's allowing for fluids to come through and react. Like I mentioned, that oxygenated fluid is what's supplying oxygen to form that hematite. So the next element, or the next mineral I want to take a look at is stulpnolane. So in this graph, you can see that in every sample that we have pyrite, we don't have stulpnolane. In every sample that we have stulpnolane, we don't have pyrite. So why are these two mutually exclusive? And hematite is also very common with that stulpnolane. So we see stulpnolane with hematite, but not with pyrite. So stulpnolane is a sheet silicate mineral. It's very similar to the mineral chlorite. This is the formula for chlorite, and that's the formula for stulpnolane. So they have pretty similar constituent: iron, magnesium, silicon, oxygen, aluminum. But the one difference is that stulpnolane actually has essential potassium in it. And this is just a trend showing, actually here, this one's better. So I want to identify what kind of trends we see in the stulpnolane mineral. So we see that I have three elements plotted here. We have the orange line is for aluminum, the brown line, the bottom is potassium, and the top line is for iron. So we see a decrease in iron, we see a decrease in aluminum, but we see an increase in potassium. So if you remember before, when I was talking about that potassium feldspar, we see a decrease in potassium and an increase in aluminum, which is the exact opposite thing we see in the stulpnolane. We have aluminum going down and potassium going up. So what's happening here? It's very likely that the potassium in the potassium feldspar is being used to actually grow that stulpnolane, and same with the aluminum. So in this figure, we have two grains that I've highlighted. The pink is the potassium feldspar, and the green is the stulpnolane. And you can see that they look very similar, the grains actually. They're starting to, the stulpnolane is kind of elongated and blade-like, and that feldspar is too. And normally it doesn't form in this sort of blade-like pattern. So what's probably happening here is that stulpnolane is forming from like chlorite that I mentioned, which is very similar, and it's taking potassium from that potassium feldspar, and the hematite is acting as a source for iron. So this kind of image, I really like this one because this puts everything all together. So we have potassium feldspar up on top, we have stulpnolane right there, we have another one there, and we have hematite. So remember I mentioned that the pyrite actually reacts and turns into hematite, which is probably why we don't see any pyrite in this sample. That hematite grain at the bottom probably was pyrite originally, and now it's been converted into hematite. So putting all this together, we have this kind of flow chart that I've made that explains the story of what's going on here. So we had pyrite reacting with maybe some oxygenated fluid to form hematite and sulfur gas. The sulfur gas left, which is why we don't see any other sulfur minerals. And the hematite went on to react with potassium feldspar, maybe chlorite, also assisted with some oxygenated fluid, and eventually forming our stulpnolane grains. So that kind of gives you an overview as to how we get all these different types of minerals. So conclusions, did we answer the questions we set out to? I would say so. We found evidence for fluids. We see the feldspars are cracked. A lot of these reactions that I put out, that I explained to you guys, a lot of them would be much easier facilitated with some oxygen fluids, so that's all evidence supporting that. The formation of stulpnolane, we can hypothesize that to be a product of the formation of feldspar and chlorite. The mechanism that I probably think that is most likely happen with this is grain boundary replacement and dissolution. So grain boundary replacement means that the edges of certain grains are being replaced with this other mineral, and dissolution means that elements are being dissolved by fluids and recrystallizing elsewhere. So those are pretty likely formational processes. And we do see a lot of these minerals, like stulpnolane included and chlorite. These are all sheet minerals. They're weak, they're platy, and that would definitely contribute to the weakening of a uniform material like a meta-arkose that I talked about before. So some further regions of research, we could maybe take a look at some whole rock compositions, maybe look at compositions from the gneiss and the marble, take the whole thing section, maybe see if we can get a more cohesive structure. I was, of course, only looking at this one meta-arkose layer, the Pohog quartzite. So it would be interesting to take a look at everything and put it all together. We could investigate the source of pyrite. Me and Dr. Garapik talked about it for just a very brief moment. It's possible that there was sulfur in the ocean water between that basin that could be a source for the sulfur for the pyrite. And that last mineral I mentioned, monazite, it is actually an interesting mineral because it actually takes up a lot of radioactives in it. So we have stuff like cerium and thorium found in monazite, and we can actually use that for radiometric dating to find out like direct age constituents. So those are all possible future directions that I could take with this. But for the most part, yeah.